some work that we've been doing recently about trying to bootstrap thermal correlators in CFT. So here's a fun fact about thermal correlators, that even one-point functions are non-zero. So when we are at 0 temperature in flat space, one-point functions are just 0 except for the identity operator. But at finite temperature, an operator can have a thermal expectation value, which is given by this, where z is just the trace of e to the minus beta h. We can expand this in energy eigenstates. Okay, so we see that the thermal one-point function is an infinite sum of 3-point functions. In a CFT, this quantity would be fixed by some OPE coefficient. But the point is, in order to compute this, you need all of these numbers to be able to compute it. So the goal is to somehow directly compute these guys without having to do this infinite sum. And the way to do that would actually be to consider a 2-point function. So let's consider two operators and consider their Euclidean correlation function like that. So tau is Euclidean time. So this is 1 over z, trace e to the minus beta h. We insert the definition of a of tau, which is e to the tau h, a e to the minus tau h, b. And we can do an analogous spectral decomposition, sum over m n, e to the tau minus beta em, e to the minus tau en, am n, bn m. So I just inserted complete sets of eigenstates. Note that since ENs are unbounded above in general, in order for the sum over n to converge, tau must be positive. And in order for this to converge, tau must be less than beta. So this expression actually only defines the correlator for tau belonging to the interval 0 to beta. And we extend this periodically for bosonic operators. So if A and B are bosonic operators, we define this function outside of this range by periodicity. An interesting property of this is we can interchange the sum over m and n and deduce the following elementary identity, sometimes called the KMS condition. A of tau b is equal to b of beta minus tau a. Okay, this we just get by flipping m and n. So in particular, we would be interested in the case where the operator a is a of x and b is the same operator but at position 0. So we get that this is equal to a of beta minus tau comma 0 and a of x. So let's denote this object by g of tau comma x. This becomes equal to g of beta minus tau comma negative x. Now, usually for this talk, we would be in 2 dimensions on higher. For specificity, let's just restrict to R2 times S1. So we will be discussing 3-dimensional conformal field theories. And whenever we have more than 2 spatial dimensions, there is a purely spatial rotation that takes a given point x to minus x. Not every point x to minus x, but pairwise we can do this. So therefore, this is also equal to g of beta minus tau comma x. Okay? So this is just called the KMS condition, and we will be using it later to derive some kind of a bootstrap program for the thermal correlators.
You haven't just used the Lorentz invariance?
No, these, yeah. Well, for this process, no. This is just rotational invariance on R2. But like for this talk, I will be sticking to Lorentz invariant CFTs. Sorry? The only thing you will not, the only case in which you will not have this is when you're R1 times S1. So here you do have it. This is, and all the correlators will be Euclidean correlators. So this S1 is the thermal circle, R2 are the two spatial dimensions. Okay.
So the question was that you can, by pi rotation, flip the sign of two guys in a plane, but not the third guy.
Yeah, yeah, yeah.
Things like that.
Yeah, but the point is, I want to look at some x, and I want to take that x to minus itself. I don't want to take every x to minus itself. I just want a particular x to go to a particular minus x, and that I can do in any dimension, just to make this argument. Okay, perfect. So what we do is, in usual CFTs, we have the OPE expansion. So we can actually write this 2-point function in terms of 1-point functions. And so that will work by the following. So let's represent R2 times S1 as a strip. So let's call this 0. This is beta. So this is the tau direction. And one of the points is inserted here. It's periodically identified. And let me, for now, put this in the middle somewhere. And we have 2 points inserted, phi and phi. I can, if the points are super close, are closer than, let's say, order beta, I can draw a circle, a sphere like this. And I can do the path integral inside of this disk. And since this space, R2 times S1 is flat, this is the same path integral that I would have done on R3. So therefore, the same OPE works on this space. It's exactly the same. So I can write the OPE, let's say phi of x, phi of 0 is f phi phi o mod x to the minus 2 delta phi plus delta minus L times x mu 1 through x mu L times the operator O mu 1 through mu L. So O is an operator that has spin L. Notice that the 1-point functions are translation invariant. So when I take the expectation value on both sides of this equation, the only things that will contribute are basically the primaries. Because the descendants you get by acting with derivatives, and since the 1-point functions are constant, the derivatives kill those terms. And now, so yes?
Would a higher complicated representation appear in the OP now?
No, the OP is still the same. So if you had like spinning operators on the outside, then I think the OP is the exact same as the flat space. So it's only even spin guys, for example, appear in the identical phis and so on. Is there a question there? No. Anyway, okay. So now we take the 1-point function, and by Lorentz invariance, the 1-point function of O1 O mu L can be some number, b sub O, divided by beta to the delta. This is just a number, times t mu 1 through t mu L minus traces, where t mu is a vector with components 1, 0, 0. So it is the time-like unit vector. And that's it. So we take the expectation value, and we have to contract these x's into these t's. And what that gives is a Gegenbauer polynomial times this number.
Which is like some generalized Legendre polynomial.
Is some, yeah, generalized Legendre polynomial, yes.
With some dimension it is a Legendre.
In this dimension, it is the, yeah. Okay, so what we basically get is this g of tau comma x is a sum over operators. And I will now, from now on, set beta to 1. So I can get rid of that. So it's b sub O f phi phi O mod x to the minus 2 delta phi plus delta times the Gegenbauer polynomial L with index nu and tau over square root of tau squared plus x squared. Nu is d minus 2 over 2.
I'm really sorry.
Yes.
For coming late. I mostly followed everything on the board except for this last Gegenbauer comment. Can you just repeat?
Yeah. So basically what we have to do is take this formula and stick this into here, because I'm going to take the expectation value of both sides.
Okay.
And these are some unit vectors, and they contract with these x's. Sorry, I should have put these downstairs, but. And that just picks out, some function of the x's, which depends on the angle with the time direction. So this.
Sorry, this is all at zero temperature here, right? If I understand, where's the
This is the non-zero temperature. The fact that 1-point functions can be non-zero at finite temperatures. The OPE is still the zero temperature OPE, but yeah.
Sorry, beta, yeah.
Yeah, beta is the inverse temperature.
The fact that O is traceless makes it complicated.
Yeah. It's a spin L, yeah. For example, for the stress tensor, this is maybe too low. So for the stress tensor, you would have something like T mu nu equals B sub T over T to the D times T mu T nu minus 2 over sorry, beta minus 2 over D delta mu nu. So this sort of, T00 is the energy density, T11 is the pressure, and this tracelessness condition relates the energy density to the pressure. So that's what this minus thing builds in.
Yeah, for a moment, had that not been traceless, then it would have just been some trivial monomial.
Yeah, some trivial monomial, yeah. It would be like, if this was just this term, it would be tau to the L. Yeah.
Sorry,
Yes.
just to make sure, B0 in general will depend on which operator. That is, as you change L, B0 will change.
It just depends on the operator. So every operator will have a different 1-point function.
Let me just check
Yes.
that ICTS can see the whole ball. ICTS, can you see everything? Can you see the ball all the way?
Yeah, up to trace, I can see trace, but not the traceless.
Oh, it's minus traces, yeah.
Okay,
Oh, no.
don't
Okay.
use the last.
Okay, yeah, I'll stay away from there. Okay.
I can see delta mu, but not delta mu.
Okay.
You're clairvoyant, Rajesh.
Okay, good. I'll stay away from there. So when you contract those x's into those t's, the vectors, you get this Gegenbauer polynomial, which is a polynomial of degree L, and this nu just labels some stuff. It is just the angle. So if this is tau, this is the spatial separation, then it's the cosine of this angle. Yeah, it's just the cosine of that angle. Okay, very good. So now what I would like to show you is an actual thing in mean field theory. So what are these BOs in mean field theory? So let's compute them. So by mean field theory, I just mean there's a Gaussian scalar, but it can have any dimension, not necessarily the free dimension of dimension delta. Sorry? Nu is just dependent on the dimension. So for dimension 3, it's 1/2. Dimension 4, it's nu I've just defined. That doesn't. L is the labels the operator. So the way the operator enters is through this delta and through this L, and through the OPE coefficient.
Sorry for this, but B0 also depends on it.
Oh, yeah, this also depends on it. Yeah. Yes. Yes, okay, so then so we know what g of tau x is in this case, just by the method of images. So this is just sum over k belonging to integers into the minus delta tau plus k squared plus x squared. Okay, this is just the answer. And note that the series expansion of this is the definition of the Gegenbauer polynomial. So when we do multipole expansion in electrostatics, we basically have terms like this, which we expand into the Legendre functions. So we can expand this into a bunch of Gegenbauer polynomials. So what you get is the following. Sum over j equals.
Sorry, Raghu, I missed
Yes.
the last bit. What are you computing now?
This is the 2-point function of this Gaussian scalar field.
Oh, this one. Yeah. In free field.
In free field theory with this generalized dimension, and beta is 1. If I had kept beta, this would be k times beta. Yes. Yeah, yeah. It's just you periodically extend it. So this, you can do the expansion. Sorry. So this is a double sum over k and j, and we get this expression. Note that crucially this thing that appears in the Gegenbauer here is the delta, not nu. So this is not quite what we want. You have to re-express these Gegenbauers in terms of the Gegenbauer with this new index. So that you can do. There is some expansion of a Gegenbauer with index delta in terms of Gegenbauer with index nu. Okay, and no. This is new here. So the new sort of the coefficients of the polynomial depend on that thing. So there is some complicated formula that relates. I'm just expanding this guy. And my goal is to write this formula like this so that I can read off the BOs for the thing. And also, let's just call this combination AO because the only thing that appears is the product. Okay, so you can turn this crank. You can write this in terms of those Gegenbauers, and what you get is the following. You get that G of tau comma x equals 1 over mod x to the 2 delta. So that's just the identity term with k equal to 0 plus sum over j equals 0 to 4, etc. Sum over L, let me call this L. Sum over n equals 0, 1, 2, etc. times the CL nu of eta times mod x to the 2n plus L times this A sub O, where A sub O equals 2 times zeta 2 delta plus 2n plus L times L plus nu delta sub L plus n delta minus nu sub n divided by n factorial nu sub L plus n plus 1. So this bracket is the Pochammer symbol, which also appeared in the talk yesterday. And so you can recognize this 2n plus L. So the dimension of this operator is 2 delta phi plus 2n plus L. That is just phi box to the n bunch of derivatives phi. And so this object is the 1-point function times this OPE coefficient of this operator. Okay, so that's the answer. So we've got something. Let me just give a few.
Sorry,
Yes.
I'm a bit lost.
Yeah,
here.
yeah. Go for it.
This is delta phi. Phi was the. What was delta there?
This delta was the thing that's appearing in the OPE. So there is an OPE of phi phi.
I got it.
Yeah.
Thank you.
Yeah.
So you went from delta O.
Oh, yeah. This is
Yeah,
delta
I got
O.
it, yeah.
Delta O minus L of O. Yeah. So basically, this is like phi phi OPE goes into this operator, and this gets a valve. Okay, so let's note a couple of things. When phi is a free field, that means delta equals nu, delta phi equals nu. Then box on phi is 0. They're the equations of motion. So, and you see that there's a delta minus nu here. So the only family that you will get here is with n equal to 0. So for a free field, by that I mean delta phi equal to nu, this formula will simplify to sort of 2 zeta, 2 delta, 2 nu plus L times, I think the rest of the thing just goes away. And yeah. I can write it down, but I don't have it in front of me. The OPE coefficients are known. You can write it. It will be some expression like this.
Taylor series, right?
Sorry?
The OP coefficient by just taking O and expanding it at Taylor.
Yeah. So those are known. Yeah. BO is like here. So if there's a stress tensor, it gets a VEV, which is determined by the symmetry up to a number.
Oh, okay.
So it's the energy density kind of for the yeah.
Sorry,
Yes.
this is the continuation of that equation, right?
Yes.
You
From here
summed
you go
over
here.
the K's, or what happened? I'm sorry.
So we did.
Index?
Yeah. So there was some rejuggling of the indices.
Okay.
The first thing was that this delta got re-expressed in terms of nu, and then a bunch of indices got renamed. Yeah. And in the end, you get a sum over the spectrum that you expect.
This K has disappeared. So on our
Yeah. So, but there's like L and N. Yeah, there's some relabeling of indices going on.
So
Yes.
suppose I just want to directly compute the one-point function of this operator
Uh-huh.
in thermal equilibrium. Could I do that by just taking the limit of this two-point function and doing a subtraction?
By taking a limit of this 2-point function, but all of those would contribute. So how would you pick out the individual?
Well, you want this at where the locations of the phi's are the same, right?
Yes. Yeah.
So you just take them.
Maybe, yeah, and hit it with a bunch of derivatives, and and take the coincident, yeah. Good. Yes. So this is the answer
Yeah,
in this, yeah. And for example, for the case for d equals 3, what we are focusing on, nu is a half. So for the stress tensor, in particular, it becomes 2 times zeta of 3. For L equals 2, d equals 3. So this is the energy density in this sort of convention of the free scalar field. Now, we will reproduce this using this thermal Froissart-Gribov formula that I will present in the next part of the talk. But right now, I will just note that Subir and some collaborators computed the same number in the large N Wilson-Fisher fixed point. In 93 is a paper titled Polylogarithm Identities in Conformal Field Theory. And for the Wilson-Fisher at large N, you get N times 4 by 5 times zeta of 3 for the stress tensor. So it is some exact number that is known, and yeah.
By the way,
Yes.
here for you is number of space or
Space time.
L is what?
Sorry, L. N was 0. Sorry. Yes. Oh, capital N just multiplies this. O n Wilson-Fisher. It's in the large N limit. No, it's d equals 3. So d equals 3, large N, you get this. Epsilon is 1.
So, sorry,
Yeah.
just to continue
Yeah.
roughly to understand how I would compute this one-point
Yeah.
function. So if I took that object, I would get lots of divergent things.
Yeah.
But then I would also get factors of beta.
Mm-hmm.
And then you isolate the term that is pure beta, no divergence, no zero as the things come together, and that would give you the one-point function. Right?
You want the term with beta to the dimension of that operator.
Yes. So, so you will have delta x to the dimension of the operator.
Yeah.
Everything will be with delta x and beta.
Yeah.
There will be some negative powers of delta x, some positive powers of delta x, and some pure beta.
Pure beta, yeah. You want the pure
You
beta.
just want it
Pure beta, yeah.
The subtractions get rid of the.
Yeah,
You
yeah, the U.
normalize the operator.
Yeah.
Another way we just do it by method of images, right? Just take an infinite images of all this operator and contract.
Yeah, but you know the operators are at coincidence points.
No,
You get divergence. You have to normal order of
For the stress tensor, this is how we normally do it.
Yeah.
Yeah.
Right. Yeah. Okay, so yes,
About how you only end up having always better primaries. So is that
yeah,
so basically this will be the subtraction with the type of the primaries, not with the 70%. Like
yeah,
these kind of operators.
yeah. I guess it's the usual thing that makes it traceless.
Yeah, the subtraction is such that the 1-point function at 0 temperature
Is 0, yeah, yes, yeah.
So no mixing with anything. That's what it is.
Okay, so just a passing comment which I just discovered recently was that this coefficient here, this 2 and the 4.5, was conjectured by Cardy to be an RG monotone. I haven't had the time to sort of fish whether that was actually borne out or not, but
I was about to ask you that.
Yeah.
How is it related to the central charge, you think?
well, in 3D there is no central charge,
So
but
in 3D there's no central charge.
yeah. So I mean, in 2D this would be exactly some central charge. This is like the Casimir energy.
Yeah, because you could do some conformal.
Yeah, but in 2D, yes. So Cardy had conjectured that this coefficient under RG flow decreases monotonic. I don't know if that was borne out or not, but
Just very quickly, in this 2D, is there an exact relation between C, which you can get, I can't do it in my head,
yeah.
to some conformal transformation of the symbol?
Yeah, yes. Because there R1 times S1 is the same as R2. So there all the thermal expectation values are just known. Yeah. Yeah. One.
I square over 2 is some such thing. I mean, I'm not
Sorry. Sorry.
How did Subir and company get that?
I don't know. I don't remember off the top of my head. Yeah, they were doing it through some Feynman diagram in the large N. Sorry? Yeah, exact answer. By sort of rearranging some terms and so on. Okay, side note also. So one note is that if I take the L equal to 0 guy in the free field theory, just phi, the phi squared operator, you get 2 times zeta of 1, which is infinity. And that is related to the fact that in 3D, on a circle, when you reduce the scalar operator, I mean the free scalar in 2D is weird because of some IR divergences. So that just is a peculiar thing. If you take L equal to 0, and nu is still 1/2, so this is the so this stress tensor was phi d phi. If you just take phi, which is the phi squared operator, you get 2 times zeta of 1, which is infinite. But that has to do with the peculiarities of the scalar on non-compact space in 2 dimensions. Okay, great. So now let's move on to the main part of the talk, which is this thermal Froissart-Gribov formula. And I will keep this up here. And yesterday we were having a discussion about, in Parijat's talk, about what basis of functions to expand the 4-point function in. Here, these Gegenbauer polynomials are very nice. They're already orthogonal and everything. You don't need to sort of do some fancy harmonic analysis. And basically, you can multiply it by its conjugate and invert this. It's very direct. So I will multiply this. So basically, you will get g of tau comma x. Let me multiply it by cj of nu, and this the same thing. And let me integrate over d theta. There is some normalization factor for the Gegenbauer polynomial. Theta was that angle between tau and x. And so this will pick out some power of x and this thing. I can further integrate 0 to 1 dr over r to the opposite power here, 2 delta phi minus delta. And let me define this object to be a delta of j. So 2-point function. We multiply it by this Gegenbauer and this power of r. And this guy would have poles at the physical operator dimensions with residues given by these AOs. It just follows directly from yes.
Mod x is the same as square root of tau squared plus x squared.
Yes, 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 yes. Sorry.
And r is that division.
Yeah. R equals. Sorry, thank you.
It's a very transform, is it? You go from tau and x to some j and
So when you multiply, let's insert the G expansion here. So by the orthogonality of Cj, this will just give a delta Lj. So this will pick out a delta Lj. And this guy, because of the dr over r, will give poles when this delta is equal to that delta. So yeah, I can put here delta of O, L of O. So when delta equals delta of O, you will get a pole. And the residue will be equal to the 1-point function. Okay, so let's draw this. In general, this would be some, yes, sorry?
This whole combination.
This combination, this B times F. Yeah. Okay, that's very good. Let me introduce some other coordinates now, which will be useful in the analytic continuation. So this would be called the Euclidean inversion formula. And we want to sort of go do a contour deformation and get to some kind of a Lorentzian. Yes.
But if this is formula in from 0 to 1 or we have it's not a Cauchy form.
No. So this is just, let's just try. So let's do dr over r to the 2 delta phi minus delta. And let's take one of these operators here. So it's r to the minus 2 delta phi plus delta O. So that's just 1 over delta O minus delta. So it's just this pole. Yeah. It's like a Laplace transform. You can yeah, it's a Laplace.
So what's the motivation to even go to Lorentzian signature? I mean, in Simone's formula, the Euclidean formula sort of doesn't really work with the very good convergence properties. And
Yeah.
so I mean, that was why he went to Lorentzian. So here, is there a similar?
Right.
It seems like this formula is just perfectly good.
Yeah. So this formula is perfectly good, except that still it's not defined at j, not an integer. So one motivation is to have it analytically away from it. But the other motivation is sort of getting ahead of myself is when you're in the Lorentzian, when you have the Lorentzian formula, you can go to the light cone limit and you can sort of isolate these double twist operators, the 1-point function of these double twist operators, which can be nice because these are the kind of things that you would get from the light cone regime.
so you're not doing finite time, real time at finite temperature.
No, this is just purely Euclidean.
Euclidean and then totally influent when you go in.
The Lorentzian here will be slightly different, as I will say. Yeah, it's not the usual real-time correlation functions. Okay, so let's define a variable z to be tau plus ix, and a variable z bar to be tau minus ix. Note that usually the I is with the tau, but here it's with the x. It's because this tau is special here. So let's also call this r.
X is mod.
X is, so we can, by rotational invariance, we can put it into one plane. Just we can get rid of the other direction. So it's only one of the things matters. This is r e to the I theta, which is also equal to r times w. So this equation defines w. And the analytic continuation we would want to do is to take w away from the unit circle. Okay, so R is real number. R is always this. You can think of also analytically continuing R, but we haven't sort of thought about that. It's this usual thing where we think of analytically continuing time, but we don't analytically continue space in the usual business. Okay, very good. So So yeah, so let's now try to first do it in just d equals 2. We'll see what happens. So let me draw this out. So this is the W plane. Here is the unit circle. So right now we are integrating along this contour. And let me also draw the z and the z bar. So this is the 0 and beta. This is one operator here and its image. This is the sort of the z bar axis, and this is the z axis. When you go to, this is a cartoon. So this point is z equals z bar equals 1. And this is z equals z bar equals 0 point. So note that in general this G will have branch cuts when z and z bar equal 1. It's when the second operator hits the image, hits the light cone of the image. So there are branch cuts starting at W equals 1 over R to infinity. So this is, notice that R was less than 1. So yeah, the 1 over R is bigger than 1. And then there's a branch cut here, and there is a branch cut here. This is at R. W equals R. So when W equals R, Z bar equals 1. When W equals 1 over R, Z equals 1. So let's look at 2 dimensions to be simple right now, because everything becomes. Yes. Yes.
Too fast. Can you explain the branch cuts again?
This
Ends of the branch cuts.
the
So
end.
one of the branch cuts was coincident with it?
The branch cuts are when there is a second operator here that's floating around,
Yeah.
and when kind of this operator goes through one of the light cones of the image, so there is a periodicity. So when it goes through z equals z bar equals 1, you expect some singularity. Either z equals 1 or z bar equals 1.
Sorry,
Yes.
but you're taking the 2-point function and continuing it, if I understand, the expectation value of the 2-point function.
Yes, we will continue this g. This g.
Okay.
So this g is a function of tau and x, but I can think of it as a function of z and z bar, just because of this. And then I can think of it as a function of rw and rw inverse.
Yes, yes.
Yeah, so we are analytically continuing in this variable. And the integral over theta is an integral over w. It's an integral over that unit circle in the w plane. Yeah.
So when x was real for a moment,
Yes.
before we did anything,
Yeah, yeah.
analytic integration,
Yeah.
then everything was Euclidean.
Everything was Euclidean.
So the only branch cuts were at the operator or its image points.
At the operator, or yeah.
So the branch cuts were at z equals 0
And
and z equals 1.
yeah, and so on. Yeah,
Okay?
exactly.
And now you just make that whole statement that way.
Yeah.
But that, I mean, I have the same question as Shiraj, because if you just had singularities at z equals 0, 1, 2,
Yeah.
I'm not quite understanding. Now, W there, I'm not understanding.
Yeah. So on the Euclidean section, w always has absolute value 1.
Mhm.
So if I go away from the circle in w, I'm going away from the Euclidean
Okay,
section.
I see.
Right? So w is e to the I theta. In this formalism, when x is purely real, w is just e to the I theta. So drawing the complex w plane already, sort of the orthogonal direction, is going away from this section.
Okay.
And just to be totally clear,
Yeah.
so can you explain how you got the endpoints of the branch cuts in the W plane?
So it's here, z is r times w.
Yes.
So that equals 1 when w equals 1 over r, and minus 1 when it's minus 1 over r, and z bar equals 1 is the other one.
I'm sorry, why
Yes.
is d equal to 1 a branch cut? I missed that.
So I mean, I'm making an analogy with, so So the-
What
the-
happened Z bar? Obviously, said the actual image point was at z equals 1 and z bar.
yeah, and z bar equals 1. So but when you do the Lorentzian thing, right, each of them can be, it's, sorry, this is the statement that if z times z bar is 0 in Euclidean space, then each of them has to be 0. But if z and z bar are independent real numbers, then they can just be 0. Yeah.
But 0 is a bit different from 1.
Uh,
Z was 1.
sorry, z minus 1 z bar.
But sorry, there could also be a branch point as z equals 0, z bar equals 0, which is essentially that hitting the like one of the, not the image, the exact image.
Yeah.
What happened to those branch?
So z equals 0 sits at r equals 0. So I can put that in the r variable. So that would correspond to sort of when this thing kind of shrinks to a point and this goes off to infinity.
No, but z can be 0 without z bar being 0. And that's the branch delta.
Yes. Oh. Yeah, z can be 0 without z bar being 0. That would correspond to sort of w equal to 0.
Right.
Yeah, which is on this locus already. But
they're not there. The branch there. So that would mean that w equals 0 and w equals infinity.
yeah. As you see, there's a different branch. Oh yeah, yeah. Okay, yes, you're right. I should just simply draw this as two branch cuts. Yeah, you're right. I mean, I should draw this as going from minus r to 0 minus and 0 plus to r. So r 0 minus r. Yeah. So it's like that. So yeah, precisely. So yeah, 0 to r. Yeah, this. Yes.
It's like relatively different numbers.
Yes. That is different. Yeah. Okay. So let's just see in d equals 2, this is very simple. So in particular, note that this tau over, so this polynomial, this CL of nu of theta is just cosine of L theta when nu equal to 0. So this is equal to w to the L plus w to the minus L over 2. Because w is e to the I theta. So this is just w to the L plus w to the minus L over 2. So then I can substitute that in here. And now you see that this naturally comes into two types. This part is dying towards the origin, and this part is dying towards infinity. So I can split that integral into two parts. One will be this whole thing times w to the L plus some other thing times w to the minus L. For this w to the L part, I can make this contour like this. Like and for the other one, I can make it sort of this like that. And now I will make this assumption, which we haven't fully proven yet. So this is sort of, I should have said, this is still work in progress and we don't fully understand. So we will drop the arcs both at 0 and at infinity. This is like an unproven assumption, and we have sort of tested it in a few cases, but it's not completely on a rigorous footing as the boundedness in the Reggie limit of the usual 4-point function. Okay, good. So we can just do this and make those contours, and that will give us our final formula. So let me just say that a similar decomposition of the Gegenbauer polynomial is possible in higher dimensions, where in d equals 3, you can write this CL nu of theta. So this Gegenbauer polynomial is a solution of some differential equation, which has shadow. Which one is the shadow block? Sorry.
In this principle is when you get it, you get actual block and shadow block. It could not, it may not be there, but I'm certain.
But these two you mean?
They are totally different to particular one around 0 and around 8.
Yeah. I don't know. Maybe. Yeah. So yeah, the point is that Gegenbauer differential equation has two nice solutions. One of them which dies near the origin, another one dies towards infinity. And the actual Gegenbauer polynomial is a sum of those two solutions. So we can just pick those.
Question here.
Yes.
The question from Ising is,
Yes.
I just wanted to clarify what your assumption is. You're dropping the big contribution from the big arcs.
Yeah, and this little one near the origin.
I mean, in Simon's derivation, he actually added some pieces which enabled him to drop the contribution from the big arc. Is that somehow you're differing from that derivation?
Yeah, so here we are just assuming that this 2-point function dies fast enough at infinity. Yeah, in some cases it does not, so this is like an iffy point. At least for high spin, if the spin of this, what spin of what? This j is high enough, then you can drop it. But yeah, it's not perfectly clear, and I will comment on some things later. Okay, so we can call these functions bj of w and bj of w inverse divided by 2.
Is it true for sufficiently large j that this has to work? Or
Yeah, we believe, this is an unproven conjecture, that for j bigger than 0, it should work.
okay.
And only scalars are the only iffy part. But we haven't been able to rigorously prove it yet.
Is that JL? Is that from?
Yes.
No, I'm just making.
So this bj is some, let me just write what bj is. W to the j plus 2 nu 2f1 is j plus 2 nu j plus nu j plus nu plus 1 w square. That's this guy and this I mean, there are some coefficients here which I have omitted. The coefficients depend on j and nu and so on. Okay, so let me give you the final inversion formula that we get. So notice that this was an integral over r and w, which we can recast into an integral over z and z bar. And you get 4 contributions, one from this, one from this, one from this guy, and one from this guy. And you can sort of repackage them all into this one thing. 1 plus minus 1 to the j times kj. This is a formula for a times delta of j times integral 0 to 1 dz bar over z bar, integral 1 to infinity dz over z times z bar to the delta phi minus delta over 2 minus nu. So this factor is like this r to the 2 delta phi minus delta here. It's r was z bar to the 1/2 times z minus z bar to the 2 nu. This comes from the measure under which the CJs are orthogonal. That's this thing. Times this bj of square root of z bar over z times the discontinuity in z of g z and z bar. I mean, it is actually less complicated than it looks. There's just some powers of z and z bar, which are determined by the external operator, the operator whose 1-point function we want to get, and nu. There is this bj, which is sort of the moral analog of the cj after it came from here. And then there is the g, which becomes a discontinuity because it's this minus the up minus the down.
And the left-hand side is a function which has poles at the operators.
Yeah,
that
in the
complement,
theory, yes.
And whose residues is this.
It'd be, yeah, exactly.
And so discontinuity
Yeah.
is depending on whether you're closing which
Yeah, the discontinuity is just along the branch cut because there are two pieces of the contour. So the integral contains g here minus g here. So
And I've forgotten, when were you closing using the outside, and that depended on?
on whether we take
this
this
part
term
of that
or
part.
this term, yeah.
Thank you.
Yeah, but all those things can be packaged into this.
So this discontinuity then is along all the branch cuts in the end, or?
So here, let me draw.
Okay.
Let me draw another picture. Actually, let me just extend this picture here.
This function bj.
Yeah, yeah,
So that was.
yeah, yeah, that was the
So
analyticity.
why doing this business was expected to give an analytic function? bj? I mean, I see that after doing all that, you got that, but
Uh-huh.
was that an expectation that you found the one to do this double discontinuity and so on?
It's just inspired by the usual, tricks of the. This is what.
Motivation why doing all this? The expectation, I mean.
No, we just basically copied the steps and got something. I don't know. Yeah.
Right. So this is for free theory, right?
No, for any theory. Yeah. The input is that you have this discontinuity of g, and you need to know the g in order to do this integral. So, yeah. But you don't know g for a generic theory.
And what was KJ? Sorry.
So yes, I didn't write it. Kj is just some constant that comes from normalization of these Gegenbauer things. I guess maybe they can't see there.
Is it possible to write KJ also?
It's up there.
Ah,
Is a question?
Hello.
Yes, Rajesh.
Yeah. So the formula, the Euclidean formula you started with on the left-hand side.
Yeah.
That's very much like a partial wave expansion for ordinary, in ordinary scattering amplitudes where you expand in terms of Gegenbauer polynomials,
Yes.
right?
Yes.
So there is the original Froissart-Gribov formula which writes things in terms of the other solution that the Gegenbauer polynomial. I mean, the Gegenbauer polynomial is a solution of a second-order differential equation, and then you can rewrite this in terms of the other solution, which is analytic in J.
Yes.
Does this amount to exactly that?
Yes.
Or is
It's
so the BJs are in a sense the general, the other solution.
yeah.
Right?
Yes. Yes. That's exactly right. Yeah.
Okay.
Yes. Yes.
Someone clearly has a good education. Never mind.
Yes. The point is we can use this formula even when j equal to 0, but then we should be careful about keeping these big arcs at infinity. The point is we are doing some integral over w, and it's a contour integral. So if in the end the integral went like dw over w, right, then you can't drop the arc. If it goes like any power of w that's faster than 1, like 1.1 or 1.2, then you can safely drop it. But if it is like dw over w, then you can't drop this arc. So you have to be careful, that's all.
Then this doesn't quite apply.
Well, then you just add a term plus the, or you can, or you can just use the original one, this one.
The pole also, the KJ,
The pole,
gamma.
pole, oh, j equal to 0 is not a pole here, gamma of 1 is just 0. Yeah, yeah. Yes.
So the fact that you are dealing with a single operator allows you to do this analytic calculation, right? Because you have placed the, I mean, you have an operator and you were thinking of placing it on the x-axis, let's say, right? And
Yeah.
and you're doing an analytic calculation in x. If you have two operators, then I don't know how to
Well,
do this.
one operator is at the origin. There were two. There was one at the origin. Like remember this g was the correlation function of tau at the origin and the at tau at x. Two operators.
So therefore you can place the second operator on a particular
X,
axis,
yeah, yeah.
and you are doing an analytic calculation in that.
Yes, yes.
If you
No, this is only for 2-point functions. This is only for 2-point functions. Yeah, because see the 2-point functions in thermal states are like 4-point functions in flat space. So therefore, much of the kinematics of the z and z bar is parallel somewhat. The 1-point functions are like 3-point functions by the spectral expansion I wrote, like if you expand the traces. And the 2-point function is like a 4-point function. You can think of, like if you think of a heavy, heavy, light, light in the holography case, that's a 4-point function computing in flat space, computing a 2-point function in thermal state. Okay.
Sorry, so finally in this thing you take the cut across either the branch cut outside or the branch cut inside. Is that right?
So there are like a few steps.
Yeah.
You add up all these contributions. You use some z goes to z bar symmetry of the correlation function, and you end up with an integral over only essentially this one outside. Yeah.
Right.
There is some, but let me draw what I was going to draw is this range of integration in z and z bar. So let's call this the z bar axis, and let's call this the z axis. There is a 0 and there is a 1. So we are integrating z bar from 0 to 1 and z from 1 to infinity. So we are integrating in this region. But this formula automatically includes contributions from this, and this. So it's kind of an operator is time-like separated from this guy, but space-like separated from this guy. So it is this particular regime of integration which you are doing. And note that making z and z bar off the Euclidean sheet amounts to rotating x, not tau, because it was tau plus ix. So it is this funny business. Yeah. So just remember that, and I will make some comment after. So yeah, afterwards. So let's try to reproduce the Wilson. Sorry, yes.
Really sorry.
Yeah, yeah.
Can I ask you, usually, I mean, is this supposed to be the analog of the Feynman? I'm a little confused because so you had T to be a finite temperature circle.
Yeah.
Now you've gone to Minkowski space. What exactly are we calculating? I mean, if it were not periodic and I were just doing the Euclidean calculation and I continued, I would say we get the Feynman propagator or the 2-point function. And
Yeah. So what you're
what is it that you're
Yeah, what you're asking is there a nice interpretation of this discontinuity of G in terms of the usual correlation functions, right? Whether, so this is some kind of commutator. So I think it's related to sort of the spectral density of the phi's, but I haven't sort of worked it out. But
It's more like a retarded.
yeah. Sorry.
Isn't the discontinuity associated with whether the time ordering is one way or the other? Is this the difference between the
Yeah, it's a commutator.
It's
Yeah.
the commutator.
Commutator. Yeah.
Which is usually sort of up to some theta function, some retarded.
Retarded. Yeah. Exactly. So since this already come up, let me just make the point now, which is our sort of original theory lived on R2 times S1. So this is the S1 direction, and these are the R2 directions. Normally, we would compute all the Euclidean correlators and analytically continue the tau separation into time. Here, the z and the z bar analytic continuation corresponds to going x to ix. So it is like making one of these directions a Lorentzian time direction. So you have a theory on R1 times S1, that's a space, and then times R time.
And you allow yourself to insert operators only along one of these axes.
Yeah.
The origin of the axis that is not active.
Yes. You analytically continue along the axis of the separation of the 2 points.
Yeah.
Yeah.
Okay, now I understand. So isn't this a clever way in the end to compute, say, some Green's function being the retarded in a space where one space direction is actually
Compact, yeah, yes.
in Minkowski space time with one space.
Yeah.
Okay, I got
So
it.
it's some compact space-time and some time direction.
Thank you. I see.
Yeah. So then,
Raghu,
yes.
Sorry, just a vague confusion. So if you think of your original g of tau x as a infinite sum of 4-point functions of
Yes.
your, then you would have imagined that each such 4-point function should have had have a kind of Froissart-Gribov like form, right? And there's a double discontinuity. The one that Simon Caron has is a double discontinuity.
Yeah, but there.
So how come here things are in terms of just a single discontinuity? I mean,
Yeah.
Or in other words, can you take the zero temperature limit of this and well, the zero temperature? No, that's probably not what I wanted to say. But if you just view this as a 4-point function, as an infinite sum of 4-point functions.
Yeah, but I guess, yeah, the thing we are getting on the left-hand side is also not just a 3-point function. It's some sum over 3-point functions. So like Simone's formula inverted for like a single OPE coefficient. So this is somehow inverting for this A object, which is itself like an infinite sum over 3-point functions.
So somehow you're saying that that simplifies things, and instead of a double discontinuity, you have a single discontinuity.
Yeah. It's because we were just started with a 2-point function, and it had some nice expansion in just of these orthogonal polynomials, and we only needed to analytically continue in like one variable. So you do the contour deformation here.
Right. Yeah. No, I see the algebra, but I was just wondering that. Yeah. And it seems qualitatively a little different from the.
Yes. As you said, it's more similar to the original S matrix thermal.
Right.
The S matrix Froissart. Yeah. Yes.
Okay. Thanks.
Okay. So now there is this one puzzle. Maybe some people in the audience we can talk later is. So this space, we want to know about the decay of this arc, whether the 2-point function decays along this arc.
Sorry, because you tested this formula on your generalized free field.
Yeah. So I want to discuss how that pops out because it's important.
Yeah. Don't go ahead.
Sorry. This mean field theory. Yeah. Okay. So let's do that first. That's fine. So let's take that formula and look at the z bar integral. So the z bar integral goes from 0 to 1. Here are some powers of z bar. Here are also some powers of z bar. And there is this discontinuity. So let's see. So g was some sum over terms of the form m minus z bar to the delta phi. Okay, and then so we see that this guy will give a discontinuity when z becomes bigger than m. Yeah, so the discontinuity will be like 2 times sine of pi delta phi times 1 over z minus m to the delta phi times 1 over m minus z bar to the delta phi. Theta of z minus m. For a single term, this would just be the discontinuity. Now, let's look at the small z bar expansion of this thing. Let's look at small z bar. So z bar near 0. So let's count the powers of z bar. We get z bar to the delta phi minus delta minus j over 2. The j over 2 came from bj because bj had a w to the j. W has a square root of z bar, so that gives a j over 2, and the nu cancels from this thing.
Really sorry.
Yes.
Is that sum over n including 0 or?
Yes, it includes 0, positive, negative, all integers. Okay, so we get that. Right, and then here, if I'm expanding near z bar equal to 0, I can just drop this term. And here, I can also just drop z bar. So to leading order, the z bar integral just looks like this, 0 to 1 dz bar over z bar. And you see this has a pole at the double twist, the first double twist family, when delta is equal to 2 delta phi plus j. So the residue of this term will give you the correct answer. And you see how the zeta function that I had in the answer will appear. It will appear from the sum over this 1 over m to the delta phi and so on. So the punchline is that the poles come from the range of the integral near z bar equal to 0. And then how do I get the first family? So this was for denoted by phi, 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 d, 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 phi. To get phi box d, d, d phi, you would just need to expand this thing to order z bar. Right now I kept it to order z bar to the 0. So if you expand to next order in z bar, you will get a plus 1 here. And that would put the pole at delta equals to 2 delta phi plus j plus 2. And the residue of that will give you, and it works out. Okay, and similarly you can do it for the Wilson-Fisher, the 4 by 5 that I showed for Subir's calculation. There the g has this form, but there is also, since it's an interacting theory, it gets a thermal mass. There's an exponential of minus m thermal times m minus z bar. 1/2. Where m thermal is log of square root of 5 plus 1 over 2. It's the thermal mass of the Wilson-Fisher.
Sorry, this
Yes.
is, just to make sure, this is being computed in the large n theory?
Large n theory. The large n theory, again, you can do the method of images, except you need to sort of stick in this exponential decay with the thermal correlator. Now you take this, you compute the discontinuity, you stick it into that formula, and you get the 4/5 zeta of 3. So this is like a good consistency check from that standpoint. Okay, so since I have only 15 minutes left, it may not be sort of worth it to go into the details of the Ising model, but let me just sort of outline a program. So in the Ising model with n equals 1 Wilson-Fisher, 3 dimensions.
Raghu, sorry,
Yes.
Before you go ahead, maybe I'll ask a sort of a little, following up on my previous question, a somewhat ill-posed question, which is that this discontinuity is like a commutator, right? And
Yes.
So supposing you wanted the double commutator, this out of time order commutator that people have been looking at a lot, which is the double discontinuity, would there be something so a thermal double commutator, in the finite temperature double commutator, would there be a natural quantity that it would a formula like the one that you wrote down, but with the double discontinuity of the thermal correlator, would that be a natural quantity
I think
in the
I think that would be a 6-point function. I think that's a 6-point function, which is maybe too much, like a double commutator in a thermal state. So I think this already has a commutator and it's evaluated in a thermal state. So this is already like a 4-point function with, phi commutator and then one more phi, like some heavy. So this guy is like heavy, light, light, heavy, something like this.
Okay.
Yeah.
Actually, related to their previous question, though, I mean, the fact that this is only a discontinuity and not a double discontinuity, if you think about the thermal correlator as coming from a sum over heavy states, I mean, is that just because in the Simone's formula, it was a double discontinuity, but it would have been a heavy, heavy commutator times a light, light commutator or something?
Yeah.
And you're summing over all the heavies, and then that commutator goes away, and that's why you only have one discontinuity here.
Maybe, yeah, maybe that's a good way to put it.
Sorry, can you say that again, Jared?
I was just saying that
possible I'm screwing something up, but I mean, I think in the 4-point function with Simone's formula at 0 temperature, you have a double discontinuity, and in the context of this formula, that would be a commutator of heavies times a commutator of lights. Now, you're going to sum over all heavies with the Boltzmann factor to get the thermal thing, and once you do that, you're sort of getting rid of one of the discontinuities, because that was the discontinuity of the heavies, which went into the just setting up the thermal background. And so then you're left with only one discontinuity.
Okay. Right, and then as he said, probably the double discontinuity would be something that would be a 6-point,
Yes.
some more complicated, whatever, yeah. Okay, thanks.
Okay.
But sorry, if I can just, I know you should go on, but that's why I was asking, isn't it the case that your continuation to Minkowski space really corresponds to then computing in a theory which is no longer at finite temperature, but on a finite spatial circle?
Well, that's this, yeah, of if you look at the x, but this object here is literally just G computed at, this is the G that was originally defined in the thermal theory.
Right, but what would you do to that? So what I'm not clear about is, what would you do to that to compute something at real time at finite temperature?
I don't know.
I mean, that's the kind of question we're after when we
Okay.
ask about out-of-time correlators or even in-time correlators at finite temperature, right?
Yeah, but sort of the thing that we are after is we want to compute this A sub t. So I'm interested in, let's say, computing for the O2 model, like this number. What's the energy density in the O2 model? So then, like, if I can get an approximation for this G, like, I can compute this. So if our goal is not to sort of compute real-time correlator, okay.
I was just trying to, well, we should talk later as to whether you could do something to compute using some of these techniques, real-time correlators at finite temperature.
Yeah. So one comment is that, I got into this because I was interested in computing this object, as you're saying, with real time at finite temperature, but at long times and long distances, because that corresponds to giving you thermal transport coefficients, like the viscosity and the diffusion and so on. But the point is the OPE expansion has a radius of convergence, which is basically beta, is set by the size of the circle. So going to the long distance limit from this formula seems quite hard, because you have a bunch of power laws, like the OPE expansion gives you a bunch of power laws. And outside its radius of convergence, it has to somehow be an exponentially decaying function with distance. And sort of the long time physics is somehow in these coefficients, but it's not transparent how it's there. Yeah.
Okay.
But it might be possible that if you get a good enough handle on things. Okay, so what I showed you is this z bar going to 0 is kind of like a light cone limit, and that by the usual arguments, the light cone limit gives us information about these double twist families. So let's say I want to compute A of A epsilon and AT in the Ising model. Let me put it here. Epsilon is the phi squared operator in the Ising model, sort of, and the stress tensor. So let's take these as unknowns. Okay, let's take these as unknowns, and A sub 1 is 1. And let's put these.
Sorry, what was A now?
A is this B times F.
The 1 point.
The 1 point function, yeah. And let's try to sort of see what we can do here. Note that this integral over z is from 1 to infinity. Yeah.
A sub 1 was 0. Is that a different normalization than usual?
Why is it 0?
Sorry, 1.
No, it's the usual normalization. There's a 1, yeah, it's this, yeah. So note that from 1 to 2, if z goes from 1 to 2, this thing is in the region of convergence of the T channel OPE. So this is, let's say if I expand about this point is the S channel and this point is the T channel, but it only goes up to z equals to 2. Everything outside of this integral, 2 to infinity, I have no idea like how to compute it. There is no OPE channel which will give me this g in the range from 2 to infinity for z. So somehow you have to make some kind of approximation in getting this, because we have, in the general theory, we have no idea what g is like from here on. But here's the nice thing. If you look at, let's look at the powers of z that are here. So the power of z bar was this. The power of z is actually delta phi minus delta plus j over 2. So you see that for large spin, if j is large, the large z region contributes less and less. So you expect that if you just stick in the t-channel expansion here, the large spin asymptotics will be accurate. But you might mess up the finite spin guys, just because of this exponential suppression with j. So in particular, if I stick to regions near z bar equals 0 and z equals 1, I can extract some asymptotics of large j for these double twist families. Yeah.
What is the input to the formula now in the Ising model? So what do you know?
We know that this is just true.
Yeah.
And here I want to stick in for g, g computed from the t-channel expansion, which would be an expansion in 1 minus z and 1 minus z bar.
Didn't quite understand the double channel.
Okay, so let me, so yeah, this, it's, yeah, okay. So here is the cylinder, and let's say one of the operators is inserted here at the origin. There is a second operator which is here. So I can do an OP expansion, which is kind of, along this way. But if this operator goes very far behind and comes back from the other side, I can also do an OP expansion in 1 minus z and 1 minus z bar, because z equals 0 and z equals 1 are the same point. So those are the sort of two expansions. It's kind of from the operator at the origin and its image at beta. So those are the two. And that's why if you do it at the image point, you go up to z equals to 2 and no further. Okay, so we take this a epsilon and at, okay, and we stick in, so the t-channel expansion for g, I have some expansion for g, right? G is some 1 minus z bar to the minus delta phi. This is the identity operator, plus a epsilon times 1 minus z bar to the minus delta phi plus delta epsilon over 2 times some Gegenbauer of spin equal to 0 and so on, and the t and so on. So I can take this expansion, I can stick this into the thing and get,
So the process equation contains this
I will get to the,
thing that we talked about.
yeah, yes, yes. So this is g, and I can stick it into this thing and get approximations for a phi 0 n, let's say, in terms of like some 1 plus some number times a epsilon plus some number times at. Where these numbers come from is by sticking this into here and doing these integrals near these regions. Okay, so I get something. Now I can construct sort of a better expansion for g in the S channel. So g is,
What is 8 phi? That is the operator.
this is a for the operator phi d d d phi.
Oh, okay. With L of.
With L of them. The 0 stands for the n. Yeah. And phi, well, this is the a, so it's the 1 point function.
Function of this 1 point. You're computing a 2 point function of phi, right?
So,
With this exchange.
sorry, this is just computing this, which is like this 1 point function.
I'm totally
Sorry.
confused. This A is that A of O, but it came from a G, which was 2 point function of phi.
Yes. Yeah, yeah. But a is an independent
Yeah.
object. So I can compute this a sub L like
So,
this.
but it depends on what 2 point function.
Yeah, because the f comes in. It contains an f, yeah, yes. So there is this a sub L, which has this, and now I can write some expansion for g. which is like in the S channel now, it's ZZ bar to the minus delta phi. I have the epsilon contribution, I have the T contribution, but I can write this contribution now, sigma sigma 0 L, because I computed these in terms of A epsilon and AT. So I can stick those into this expansion here, and I get some expansion which only has two unknowns. It has A epsilon and AT. And now, as Abhijit preempted, there is a condition that this G of tau, let me set x to 0, has to be equal to G of beta minus tau, which means that all odd derivatives of G at the point beta over 2 have to vanish. So hoping that I have provided enough input into this equation to get a good enough approximation for G, I can get some, I can, let's say, take the first derivative and the third derivative.
I'm really sorry. Please excuse me. Why does that equation just involve A epsilon and AT and nothing else?
There we made an approximation, so we truncated. So you assume, let's say, you start with assuming A epsilon and AT as this is a bit uncontrolled, so because we're just trying to get at whatever we can.
Okay.
So there is A epsilon and AT. You stick it into the inversion formula, you get some A for the sigma sigma 0 L. You feed that back into the G, and then you try to write these equations. So you get two equations in like two unknowns, this A epsilon and AT, which you can try to solve. And I mean, you get some numbers, but which the number for the stress tensor is close to the mean field theory answer, but yeah, we don't have any kind of a cross check for this. I mean,
Can you not take 2 minus b minus b bar general for any
no, there is no overlapping regime of, yeah. There are only two channels, and you're restricted by this. Because if your point is very far away, then there is just no OPE. If your points are separated by more than beta, there is no OPE.
And you are doing this in equal total space-time
Three.
density 3, right?
Yeah.
And if you work with the ON model and the Ising model in the universality, same universality class as the phi-4 appearing fixed point.
Yeah.
Right? But suppose I try to look at the large N version of that, is this truncation better and better justified in some sense in large N? I'm just trying to understand the system.
Yeah. I think for all the ON models, this is
No, because large N is almost free. Like tail end effect.
So everything should, that's what I was saying.
but the large N, for the strict large N, you have the formula for G of ZZ bar with the thermal mass, and then you can just stick in the exact formula there, which is how we got the 4/5. Yeah. So if you,
Take that, I'm sorry,
Yeah, yeah.
the Ising model, which is what is it, N equals 1 or 2 or whatever?
yeah, it is. So that is what I was trying to look at, if there have been some Monte Carlo numerical studies of computing that coefficient for the Ising model. And it seems that nobody has, at least I asked a few people, and nobody seems to know.
Is this an experimentally measurable quantity in the Ising model?
It's the energy density at finite. So yeah,
You're asking
I
if
don't-
it's UV finite?
Not even sure. I mean,
it is UV finite. It is UV finite, yeah.
It's perfectly physical.
Yeah.
And it's never been, in the epsilon expansion you could compute it.
Yeah. So Subir has a paper in which there was this 4/5 and then the next 1/n correction, and
large N expansion, but you could also presumably
do an epsilon expansion.
expansion.
Yeah. And I haven't found, at least no numerical stuff. I mean, there were some O2 and O3 models.
Wait, energy density is just thermal energy.
Yeah.
So it's like computing the coefficients we know that the partition function is P cubed.
Yeah,
So the
it's
number we had,
yeah,
it's
and
computing
that number. Yes, exactly. It's like the energy density is proportional to that number.
Okay. So,
Yeah.
so that's what you're after.
Yeah, that's what we are after. Yeah.
Okay.
Yeah. And the hope is, like, the initial hope was, if you get enough control over these A's, then you could put them back in to construct the G, and then somehow maybe take the long distance limit and get, for example, the energy diffusion constant of the Ising model. But it seems like a bit.
Sorry, but now that I understand better, so the dumb way to do it would be to take the phi-4 theory and compute the partition function in the epsilon expansion, right? A finite temperature, isn't it?
Yeah.
That
Yeah.
people haven't done.
Epsilon
Maybe.
expansion, sure.
People are.
Most of them.
But he wants to do it as
No, I understand. I'm just saying, just in terms of trying to compare.
Yeah. Right. Yes.
Instead of doing it in 3 dimensions, can't you check this in 2 dimensions where analytic results are known? Like
In 2D, isn't this trivial?
In 2D, we know the central charge, so for the Ising model, it's proportional. In 2D, the R1 times S1 is this is usual map.
It's trivial if you take two of them to be the stress test. Because they are covered.
So isn't it even trivial for any two-point function? Can they map that two-point function to R1 plus S1?
Yeah.
Yeah, because you're not on the torus. If you're on the torus, it would be under.
Yeah. It's because your space is non-compact. Yes.
The log conventional type bootstrap, essentially getting bounds on dimensions and
Yeah, the problem is there is no positivity in these A's. So you don't have any positive, because there is no F squared and there's no like positivity. So you can't use any of the positive methods that people have been using.
So are the A's universal for the large spin operators or not? It seems like that was one of the things you wanted to study.
Well, if you look at the identity contribution, it's universal. Like if you do the light cone analysis for the Ising model, you take some low dimension data, which is like the dimension of epsilon and the OPE coefficient of sigma epsilon. And then in terms of those, you can get all the higher spin data, this low twist higher spin data.
But I mean, are the A's for the large spin operators, do they behave as a function of spin in such a way that the identity dominates and then the higher twist operators are subdominant in the thermal lab?
Yes.
Okay.
Yeah.
I mean, there are a lot of lower combination. A, right? Not B.
Well,
F separate.
he wanted the A, but the F is known. So let's just say the combination we are interested in is A. Yes.
Suppose we were
Sorry, can you repeat?
Yes.
go
So I didn't understand the answer to my question about 2D. My question was specifically related to your truncation. So if you did
Oh, the
truncation method,
2D
2D and check.
Okay, yeah, that's a good point. Okay. Yeah. We, yes.
The generalized free field is sort of like what we would do in ADS CFT
Yeah.
in the low temperature phase. But there's a second phase in ADS CFT, which is the black hole phase, in which we know what thermal two-point functions are like. Would it be interesting to apply?
Yeah, that's one of the things we were hoping to. So there is this 4/5 in the Wilson-Fisher, but there's this 3/4 in the free energy of Yang-Mills. Like free Yang-Mills versus Yang-Mills at lambda equals infinity. The free energy of Yang-Mills goes like t to the 4th times a number. And the ratio of that number to the free is like 3/4. So one thing that you could hope to maybe answer using this set of techniques is to derive this 3/4.
Okay,
And,
but I had a more structural question.
Oh,
Like,
okay.
suppose you took the two-point function of two stress tensors in a black hole backdrop.
Okay.
Black frame.
Yeah.
That is and some function which may be hard to calculate analytically, but is given by a solution of differential equation.
Yes. Yeah.
Okay. Now you could ask what operates in this generalized free field limit, all that runs are the double traces.
Yeah.
Double traces rest with
Yeah.
Presumably in this black hole phase more interesting things run.
Yeah.
What do you expect? Do you expect it continuing to run?
Well, I think you expect that all the higher trace operators will be equally important, and they would sort of resum to give you, this. Maybe I didn't understand.
For all of the multi-stress tensor states, and those are exactly giving rise to the gravitational field.
Yeah, so I think this 3/4 is the thing that you would be after if you try to do that. Like you would want to compute the expectation value of the stress tensor itself, and then all the higher trace of the stress tensor would be just powers of that.
So, the special thing about the black hole is that the actual state is thought of in terms of V1.
Mm-hmm.
Right? It's not really well described by multi-traces of the stress tensor.
Uh-huh.
So I was wondering whether you might be able to see those whether those very high energy states
might appear. Yeah. Yeah, they might. I mean, and this truncation might be very bad.
It might get some interesting conflict.
Yeah.
But he's looking at the channel where you have two operators that are relatively light in your thermal background, and he's taking basically the OP of the two light operators. So he's looking at the things that are being exchanged between the black hole and the light operators, not like the state of the heavy black hole itself.
That's why the OP was the same. Maybe the coefficients were different, but the things that came out of the
No, of course, you're right. The 2-point function would just be exact. But
I think, yeah, it's not. I don't. Is it known analytically? The 2-point. No.
But you could write
It's
a
a-
formula for it.
Yeah, there's a differential equation.
And
and
then
then
you try to analyze its
yeah.
properties.
Yeah, so it's like a big set of open questions on that sort of themes that we're also exploring. But yeah, okay, that's all I guess I had to say.